Good morning. So to close out chapter 19, we're going to make some connections here. We're going to look at the connection between free energy and the equilibrium constant. Now, why might we look at this connection? Well, if we think about what these two values tell us, right? So the free energy, right, is our chemical potential, right? It's telling us, is the reaction going to occur spontaneously in one direction or the other, right? And equilibrium constant, the value of that, tells me how far a reaction proceeds toward products, right? In other words, does it react? Does it go? So it seems like you might find a connection between free energy and the equilibrium constant. Now, there is this connection, and that connection comes from, if we look at the equation that we introduced in the last section, right, that delta G reaction equals delta G reaction at standard state plus RT ln of Q. So if we look at that reaction, if we are at equilibrium, right? So at equilibrium here, Q equals K, and we know at equilibrium that delta G equals 0 at equilibrium, then if we plug this delta G here, we're at equilibrium, right? Right? We're not at standard state, we're at equilibrium conditions, and so we plug it in 0 here. So we get 0 equals delta G at standard state plus RT ln of K now. And we do some rearranging of this equation. You know, to put one on each side of the equation, we rearrange to get this equation where the free energy change under standard conditions for the reaction equals negative RT ln of K, right? So at equilibrium, we can find the delta G value for that reaction, or the connection between the free energy and the equilibrium constant. Now, what is the significance of this, or what can we sort of get out of this? Well, so we can look at what is the significance of the value of K, right? How does that affect delta G? Well, if K is less than 1, so remember, that would indicate a reactant favored equilibrium, then delta G will always be positive, right? So, and that just goes back to the idea that if I take a natural log of a number less than 1, I'm going to get a negative number, and so when I do that, I'm going to get a negative of a negative, or delta G ends up being positive under those conditions. Or in other words, it's going to be non-spontaneous. Or another way to think about that is that it's not going to be spontaneous in the forward direction, right? It's going to be spontaneous in the reverse direction. Okay? So again, both a small k, a reactant favored k value, and a positive delta G would both tend to indicate that the reactants are favored, or again, the reaction is spontaneous in the reverse direction at standard conditions. Now, what about the opposite? What if K is greater than 1? Again, K greater than 1 would represent a product-favored equilibrium. Now, of course, under these conditions, delta G will be negative, right? Because if you take the natural log of a number greater than 1, you're going to get a positive value. And so you're going to have this negative sign. And so this value here is going to be a negative number. So that means delta G, its standard reaction, is going to be a negative number. And that will, of course, tell us that the reaction is spontaneous in the forward direction, right? Or the direction we have it written as. So again, both of those are telling me that K greater than 1, we're going to make products, right? We're going to move in the forward direction. Delta G negative, spontaneous in the forward direction, again, under standard conditions. So there's this connection here between what K tells us, what the value of K tells us, and the sign of delta G. There's a consistency there. Now, of course, if K were equal to 1, then the natural log of that would be 0, and so delta G under standard state would be 0, and if delta G is equal to 0, that means we're at equilibrium. So this is probably the rare case where it happens that equilibrium occurs at standard conditions. This is not something that we find very often, that we would be exactly at standard conditions equilibrium. But that's what the significance would be if I had a K equal to 1. All right, so now I've established the connection between the free energy at standard state and the equilibrium constant. And if we then pull in our previous equation for delta G at standard state of the reaction, so now we have two equations both equal to delta G at standard state. What if we set these two equal to each other? So we're going to start with, we're going to look at delta H minus T delta S equals negative RT ln of K. So if I do some rearranging and manipulation here, I can get this down to look something like this. I can solve for ln of K, and I get delta H of the reaction over R times 1 over T plus the entropy of reaction over R, and I have a typo here, right? There should be a negative sign in front of this, so it's the negative delta H of reaction over R times 1 over T plus the delta S of reaction over R. Right? So if you can't fill out the algebra, right, there's a little bit more detail in the book about the algebra, but essentially we've gone through and divided by negative RT to get this, and we're separating out this 1 over T part. Instead of writing it negative delta H, instead of writing it negative delta H over RT, right, we've just pulled out this 1 over T to emphasize the fact that this equation is in the form of a line, right, where y equals mx plus b. So if I were to graph the natural log of the equilibrium constant versus the inverse of the Kelvin temperature, my slope would give me a way to get to the delta H value and the y-intercept would give me a way to get to the entropy of reaction. So bottom line is, if we can measure K, the equilibrium constant, at a bunch of different temperatures and graph them, then we can have a graphical way to determine the enthalpy of reaction and the entropy of reaction. So this can be very useful. Now, it is not a trivial thing to measure the equilibrium constant at multiple temperatures, right? We did some experiments in lab just looking at calculating an equilibrium constant, but we just did it at one temperature, right? Doing that and trying to maintain a temperature, a given temperature while you do it is not trivial. It can, of course, be done, but that's not something we're going to do. So, like we've done with a couple other equations in the course, this can be sort of reformulated as what we would refer to as a two-point equation. And this just allows us to compare or estimate the equilibrium constant at one temperature if we know it at another temperature, or if we, measure two equilibrium constants and we could solve for what one of the temperature is, but it'll give us a way to predict how the equilibrium constant will change if we give two different temperatures. So essentially, we're using this with only two data points, right? Or estimating it using only two data points as a way to estimate how K can change, or if we know both K's and temperature, we could use it as a way to calculate the enthalpy of reaction if we wanted to, but it can give us the relationship between temperature and the equilibrium constant based on only two different temperatures. So this is much more useful for sort of just book value to look at the connections between the equilibrium constant and temperature, how that varies with temperature, without having to do a whole graphical analysis, right, of having to have data at multiple temperatures. So that really brings us to a conclusion of what we want to talk about in Chapter 9, looking at some of these other connections with delta G. So we're establishing connections now between free energy and the equilibrium constant, as well as the other thermodynamic quantities that we've talked about. We've looked at how to measure or how to calculate our free energy under various sets of conditions, whether they be standard state, whether they be non-standard, what it means to have it at equilibrium, etc. Now, the last thing that I'm going to do here is do a practice problem using this two-point equation. So to wrap up this section, I want to do an example problem looking at the connection between the equilibrium constant and temperature. So the problem here says calculate K, our equilibrium constant, at 298 Kelvin for the following reaction, right? N2O4 gas in equilibrium with 2 moles of NO2 gas. So remember the equation that connects these two, right, is that delta G at standard state for a reaction equals negative RT ln of K. So now that we have our equation, what are we going to do here? Well, first we need to have our delta G value, right? We're not given that for the reaction, but since we're at 298, right, we can use delta G's of formation from the back of the book to get it. We could also, if we were at some other temperature, we could use delta G equals delta H minus T delta S, and we could calculate delta H and delta S from data in the back of the book. That would be a little bit longer process, but we can recognize the fact that we're at 298 allows us to simply use the delta G's of formation values to calculate the delta G of reaction. So that's what we need to do first. So remember, our equation for that is the delta G equals our sum of the delta G's of formation for the products minus the sum of the delta G's of formation for the reactants. So if we look at what we need to do here, our product here is NO2. So the value there is 51.3 kilojoules per mole. We need to multiply that times 2 because we have 2 moles in our reaction. And we're going to minus that from the reactants, N2O4, which has a value of 99.8 kilojoules per mole. And we just have one of those, so we don't have to multiply it by anything. So if we take our 2 times 51.3 minus 99.8, we get a value of 2.8 kilojoules per mole for my delta H standard state. So now we have our delta G. So we can use that in our equation, and we can solve for K. So if we go ahead and write that in here, we got 2.8 kilojoules per mole. Now, before we go any further, we have to kind of think about what's going on here, right? Because if I were to continue to write this, my value for R, right, is 8.314 joules per mole Kelvin times my temperature, 298, times the natural log of K. But notice that my delta G value is in units of kilojoules, but in my constant, I have values of joules. So if we were to continue to solve the problem like this, we would get an incorrect answer because we don't have matching units, right? So the easiest way to fix this is just to simply convert delta G into joules. So we can take our 2.8 kilojoules, multiply it by 1,000, and we get 2,800 joules per mole. Again, will equal our negative 8.314 joules per mole Kelvin times 298 Kelvin times the natural log of our equilibrium constant. So if we go ahead and do a little algebra here, we get this side of the equation equals negative 2478 times the natural log of K, and we have still 2,800 joules per mole over here. We divide to get the natural log of K by itself, so the natural log of K equals 2,800 joules per mole divided by negative 2478 joules per mole. Of course, our units cancel here, joules per mole on top, and so we get that our natural log of K equals negative 1.13 equals the natural log of K. Now, if you don't quite remember dealing with natural logs, they are the inverse log. If a natural log is an exponential or an e to the x function, so if we want to find the term that we're taking a natural log of, we need to get rid of that natural log by taking the anti-log or taking the exponential of both sides. So we're going to take e to the negative 1.13 on this side, and e to the natural log of k. And so, of course, those two things cancel out, and we get e to the negative 1.13 equals k. So if we calculate that function on our calculator, we get 0.323 equals k. So for this reaction at 298 degrees, our equilibrium constant would be 0.323. Okay. So now we have looked at or have an example of how we might go about finding the equilibrium constant at standard state at 298 degrees Kelvin. Now, we could do this at a different temperature, and of course we would find a different value of k, right? Because we've just established back in the equilibrium chapter and also just re-pointed out when we looked at the connection between delta G and k, that k is temperature dependent, right? So this is the value at 298. If we were to do it at a different temperature, we would of course get a different value. But now we can use one value, either the equilibrium constant, and calculate delta G at standard state, or use delta G at standard state to calculate the equilibrium constant.